Okay, this is the last of the easy graphing examples. After this, we're going to delve into a lot more detail as far as taking more derivatives, finding out more things about these graphs and whatnot. So anyways, let me end with one. The numbers on this have been chosen not to be so bad. So I want to do the same thing I normally do. Graph this, find the local max and mins. Let's do radical 3 sine of theta plus cosine of theta. And we'll say that negative 2 pi is less than or equal to theta is less than or equal to 2 pi. So it's a bounded interval. Closed and bounded interval. Since sine and cosine are both not just continuous but differentiable everywhere, they're guaranteed to have absolute max and mins on this particular interval. So the first thing we want to find out are the zeros, or the x-intercepts. So for intercepts, I'll first start the x1s. We will set the function equal to 0. And then I'll try to solve for theta. So the first thing I would do would be to subtract cosine of theta. Divide by sine of theta. So now it becomes radical 3 equals negative cotangent of theta. I'm going to flip things around a little bit and arrive at tangent of theta equals negative 1 over radical 3. And try to find all the theta values between negative 2 pi and 2 pi for which this happens. Now whenever I see this, it's sort of difficult for me to tell what sine and cosine is. I don't happen to have this number off the top of my head, but this is what I do kind of remind myself. If I think of the sine part being 1/2 and then the cosine part being radical 3 over 2, you can see that those numbers do create this. And I happen to know, at least in the first quadrant, sine of theta is equal to 1/2 when theta equals pi over 6. So now this thing here is in the fourth quadrant, though. Let me put that in here. It's in Q4. Since it's in the fourth quadrant, I have the same kind of thing going on, except sine is negative in the fourth quadrant. So instead of pi over 6, this is going to be negative pi over 6. Now, there's a bunch of answers besides just that one, because we have to go all the way from negative 2 pi to 2 pi. And tangent has a period of pi. That means these are also answers. If I subtract pi from this and get negative 7 pi over 6, that's also an answer. If I try to subtract another pi from that, I'll end up with negative 13 pi over 6, but that's more than negative, or less than negative 2 pi, so I'm not going to have that. But then I get some answers by adding pi. So I get 5 pi over 6, 11 pi over 6, and then I stop there because I'm only supposed to go up to 2 pi. So this looks like my 4 zeros. So let me write these down. The accents, that's what I was finding here. They were, I'll put them in order too. Negative 7 pi over 6 comma 0. Negative pi over 6 comma 0. 5 pi over 6 comma 0. And then finally 11 pi over 6 comma 0. So those are x-intercepts. For y-intercepts, that's the easiest thing in the world. All you do is plug in theta equals 0. So for the y-int, I get f of 0 equals radical 3 sine of 0 plus cosine of 0, not theta, of 0. And that equals 1. Sine of theta is 0. So we only have the one y-intercept, 0, 1. And that takes care of that business. I don't have to really talk about domain here because even though the domain is negative infinity to infinity, this problem specifically says to limit my attention to negative 2 pi to 2 pi. So next then, these functions that make up the function we're using are differentiable everywhere. So the only way we're going to uncover maxes and mins is by taking the derivative and setting it equal to 0. So let's do that. So let's call these local extrema. So let's see what we have here. F prime of theta, this equals radical 3 cosine of theta minus a sine of theta. And set that equal to 0. I'll add sine theta to both sides. And then I'll divide by cosine of theta. So it'll become tangent of theta will equal radical 3. So one solution for that, this time I'm thinking of radical 3 as being radical 3 over 2 divided by 1/2. This way I'm thinking of cosine as 1/2 and sine as radical 3 over 2. That happens at pi over 3. Now, of course, you've got to add multiples of pi so that you capture all these because tangent is periodic with period pi. So let me add a pi in there. So I'll get 4 pi over 3. Then I'll get 7 pi over 3. That's too high. That's more than 2 pi. And then I'll start subtracting pi from each of these. So I'll get negative 2 pi over 3, negative 5 pi over 3. And if I try to go any further, I'll go farther than negative 2 pi. Let me go and get the y values for each of these. So f of pi over 3, that equals radical 3 sine pi over 3 plus cosine pi over 3, which equals radical 3 times sine of pi over 3 is radical 3 over 2, and cosine of pi over 3 is 1/2. So it looks like I get 3/2, so it looks like I get 2. All right, let me go and do f of 4 pi over 3. That will equal radical 3 sine of 4 pi over 3 plus cosine 4 pi over 3. Now this thing here is in the third quadrant, so both sine and cosine are negative. So that's radical 3 times negative radical 3 over 2 minus 1/2. That will equal negative 2. F of negative 2 pi over 3. That equals radical 3 sine of negative 2 pi over 3 plus cosine of negative 2 pi over 3. Now these are both in, this is the fourth quadrant. This didn't quite make it. No, this is actually, I'm wrong. This is in the third quadrant. So this is negative and this is negative. I don't think we need to go through that computation again. And then, in fact, negative 2 pi over 3 is the same terminal angle as 4 pi over 3. So it wouldn't surprise me if 5 pi over 3 is the same terminal angle as pi over 3. So it is. So I'm not going to bother with that. F of 5 pi over 3, negative 5 pi over 3, is the same as f of pi over 3, which turned out to be 2. So all of our absolute, and these actually are going to end up being absolute max values. The only thing I'd have to check is the endpoints, which is at 2 pi and a negative 2 pi. And if you start if you plug in negative 2 pi or 2 pi, in both cases, f of that will be 1. So 2 is the highest possible value, and they're all local extrema as well. So now I want to figure out if it's increasing or decreasing at each of these spots. So let me draw myself a number line. I shouldn't end it with that, because what it does do is it ends at 2 pi, and back here it ends at negative 2 pi. So let me go ahead and put in my points relative to that. We have negative 2 pi over 3, negative 5 pi over 3. And then we had pi over 3 and 4 pi over 3. And now let me just get increasing and decreasing for each of these. So I got to pick numbers, test points between there. Now if you think of this as negative 10 pi over 6, and you can think of this as negative 12 pi over 6, then you can understand why I might test negative 10 pi over 6. Nope, negative 11 pi over 6, sorry. And then in between here, I have between 2 and 5. I can pick any number in here, so maybe I'll pick negative 3 pi over 3, which is otherwise known as negative pi. These are always good because something's going to turn to 0 if you get a chance to do those. This is always, the easiest number is almost always 0, so I'll plug in that as my test point between negative 2 pi over 3 and pi over 3. In between here and here, I guess I'll do 3 pi over 3, which is pi. And then finally, if I think of this as 6 pi over 3 and this is 4 pi over 3, then I should test 5 pi over 3. And let's plug them each into the derivative. Where was that derivative? Radical 3 cosine of theta minus sine theta. And let's plug these numbers in. Negative 11 pi over 6. That's radical 3 cosine negative 11 pi over 6 minus sine negative 11 pi over 6. Well, it turns out that this has the same terminal angle as just regular old pi over 6. This is in the first quadrant, so both of these things are positive there. So now think pi over 6. Radical 3 cosine of pi over 6 is radical 3 over 2 minus sine of pi over 6 is 1/2. So we end up with 3/2 minus 1/2, which equals 1, but it's positive. That's all I care about. I'll put a plus here, and it's increasing. Then f prime of negative pi equals, the only sine is going to be 0 here, and cosine will be negative 1. So you're going to get negative radical 3. So it's decreasing. Cosine of 0 is 1. So you're going to get a positive radical 3 here. It's going like I probably figured it would do. And then f prime of pi will end up being negative pi and pi are the same terminal angle, negative radical 3. It'll be negative, so we're decreasing again. And then finally, we'll have f prime of 5 pi over 3. This is a fourth quadrant angle akin to pi over 3. So that's where sine is dominant. So radical 3 cosine of 5 pi over 3 minus sine of 5 pi over 3. Fourth quadrant, cosine is positive while sine is negative. So I get radical 3 times 1/2. So sine is negative radical 3 over 2, so this is a plus. And that turns out to be radical 3 again. And as we expected, this is increasing. Now I'm prepared to throw in a rough sketch graph. Let me go ahead and do it. And then I'll draw it on a real graph, but just let me show you some of the stuff you can do on your own without absolutely needing technology to help. So let's first, I'm going to lay down my zeros. The x-intercepts, what were they? At a lot of pi over 6s, so negative 7 pi over 6, negative pi over 6. So negative pi is probably right about here. Negative 7 pi over 6 is a little to the right of that. And then negative pi over 6 I'll throw over here somewhere. Okay, and then we had uh, 5 pi over 6 and 11 pi over 6. 5 pi over 6 is a little less than pi, so I'll put it over here. And then 11 pi over 6 is way over here. So those are my zeros. Let me go ahead and put these here. Dots. At the endpoints, I had a y-intercept of 0, 1, so I'll put that there. Plus, at the endpoints at negative 2 pi or positive 2 pi, you would get radical 3, which is a little higher, so I'll throw this radical 3. So we have it increasing here. Let me put the endpoint in. That's it. Negative pi over, or 2 pi radical 3. And this one is at radical 2 pi. 2 pi radical 3. Now let's throw in our derivative zeros. So I have negative 5 pi over 3. Negative pi over 3 is like negative 10 pi over 6. And this is like negative 12 pi over 6. So I know it's a little bit closer. I'll put, in case I'm running out of space here, negative 11 pi over 6. And the height of that thing was 2. Or negative 2, it depends. And what was my next one? I had a negative 2 pi over 3, which is like negative 4 pi over 6. So that's right directly in between here. Okay. And then I had a pi over 3 and a 4 pi over 3. Pi over 3 is like 2 pi over 6. So I'll put it about here. And then 4 pi over 3 is like 8 pi over 6, so it's right smack dab in the middle of these two. And then let me get their y values that were associated with those. They're all either 2 or negative 2. So I had 2 for pi over 3, negative 2 for 4 pi over 3, pi over 2. 4 pi over, I put 8 pi over 6. I didn't intend to do that, but let me go ahead and put, here's negative 2. So that's a local and absolute minimum. And then on the negative side of things, we had negative 2 pi over 3 and negative 5 pi over 3. Oh, I already took care of that. Negative 5 pi over 3. So that had a max of 2. So this must have come down to negative 2. And we'll get a graph that does something like this. Go up until you get to that. Make it even more brutal. Come down to there. Then they got to connect to that. Up through there. And then they got to make it through the y-intercept. So I got it. And then the 5 pi over 6, I believe, was a 0. So it's going to come down like that. Got that. And it ends like that. So this is my graph before looking at the computer-generated version of it. So let me go ahead and pull that up, and we'll see how the two of them compare with each other. Okay, now I've got my graph, and I can see that I made a mistake at the endpoints. Look at these endpoints here. They are negative 2 pi comma 1, so this up here should have been lower. So let me fix that. And the other endpoint too needs to be fixed up because it ends also at 2 pi comma 1. I must have been thinking of the derivative when I came up with these points. So the radical 3 isn't even a thing. Get this out of here. It ends at 1. So it goes like this. Let's check my other things out and see how they worked out for me. I have what looks like here a maximum at negative 5 pi over 3 comma 2. On my graph, negative 5 pi over 3 comma 2. There is a local and absolute max. Negative 5 pi over 3 comma 2. Then what else do I have? Negative 2 pi over 3 at negative 2. All right, and then I had pi over 3, 2. These are all matching up with my graph. I should take this radical 3 out of there. It has nothing to do with any... I figured I might do that, but let's go ahead and put you in there. It looks so sad. All right, so then we got another point here. Minimum at 4 pi over 3 comma negative 2. All of these are also, besides local, they're absolute. In whatever they are, max, pi over 3, or min. Let me just make sure I had the pi over 3, 2 up there. So these guys up here are abs, maxes, and local maxes. And these guys down here are abs, mins, and local mins. The absolute maximum value, abs max value, is 2. And the abs min value is negative 2. So that wasn't so bad. Like I said, I made the numbers work so it would be pretty easy to do this problem. We're going to get into some heavier graphing after this. We'll be taking a second derivative. We'll be talking about something called concavity. You'll see it'll provide little bitty details that we're not able to do right at this minute.